In this video, we're going to look at the gain bandwidth product, which is a commonly listed specification on many op-amp datasheets. This spec says that the product of the closed-loop gain of an op-amp and the bandwidth in that configuration is always constant. The relationship is so ubiquitously reported that it's easy to think of it as a physical law, but the gain bandwidth product actually comes from dominant pole compensation. We'll show that in this video. We're going to look at a standard op-amp in inverting feedback like we've done in the past few videos. But one change we've made is to assume that the op-amp is dominant pole compensated, so it has a single pole located at a position of 1/tau. The closed loop gain is given by the forward path over 1 plus the loop gain. And I have factored an additional 1/f out in front here, so this looks like the loop gain over 1 plus the loop gain. So this is our commanded gain 1/f, and here's the behavior of our feedback loop. We can clear the fractions from this expression, and then factor it into an instructive form. Here we have our commanded gain out in front, multiplied by a steady state error or a static state error or a static error term, and finally by a first order dynamics term. This term is sometimes called the dynamic error because if you put a step function into the amplifier, it will this results in sort of a decaying exponential that gradually goes to 1. Now it's worth noting that the location of the closed loop pole in this transfer function depends on the value of f. So here the pole for a closed loop transfer function moves around as 1 plus af changes. Because it's no longer at tau, it's now at tau over 1 plus af. So we call this effective time constant a closed loop time constant. So we know that our commanded gain is 1/f, and we know that our bandwidth is going to be given by 1 over our closed loop time constant, or 1 plus af over tau. Multiplying our gain by our bandwidth gives us this expression, and if we pretend that af is way bigger than 1, this is approximately a over tau. Now, neither of these depend on f, so this is approximately constant. But it's only approximately constant because of this expression, because of how our closed loop pole moves around with f. In particular, our closed loop pole is proportional to f, but our gain is proportional to 1/f, so the two factors cancel out. Now, if our open loop transfer function was more complicated, had 2 poles or a 0 or something in there, we would no longer have a constant gain bandwidth product. This is purely a consequence of the fact that our op-amp behaves like a first order system. By the way, there's a neat graphical way to see a constant gain bandwidth product in action. This is plots of the closed loop gain of this amplifier with different feedback factors. We know that the closed loop gain increases as f becomes smaller, but that the bandwidth over here also decreases linearly as f becomes smaller. So those two cancel out, which results in the high frequency roll-off of the amplifier stacking up on top of each other, regardless of what our feedback factor is. All of those cross over at this point where our closed loop gain is equal to 1, and so this crossover frequency is our gain bandwidth product. And by the way, since we know that our closed loop gain is equal to 1 here, that means we can find our gain bandwidth product by measuring the 3 dB roll-off of an op-amp in unity gain feedback. Because 1/1, because the feedback factor is 1, and 1/1 gives us the gain of 1. So in summary, we have a constant gain bandwidth product, which specifically is a commanded gain times closed loop bandwidth product. And that comes from the fact that our op-amp is dominant pole compensated, which is true for the vast majority of op-amps on the market. That behavior has a graphical interpretation where the gain bandwidth is the crossover of a family of closed-loop transfer function curves that scale their commanded gain up at the same time that they scale their closed-loop bandwidth down.